Welcome back to Joe's Computer Museum. Sorry about the delay in video output. Sometimes life just happens. Things got in my way. Didn't have a lot of time to work on the project. But since we're back, let's review where I was at the last point in the project. Basically, we got the primary CPU core working just in a simple free-run circuit with the hexadecimal output so that we could show what the computer is doing, just so we could see it functioning, operating correctly, to get an idea of our base theory. But since last episode, I have gone and done a lot of stuff, so let's check that out. So what do we got in here? Well, we have all of this. You can see I have several other breadboards attached. Lots of fly leads and jumper wires all over the place, and our display is showing something different from what it showed before. Before I dig into that, I do want to talk about a few things that I learned since last episode in this entire journey. First off, here I'm using Ethernet wires, or Ethernet cables, and you see some of them here too. I have that stuff in bulk. It seems to do a better job of communicating signal connections, not necessarily power, but signal. It seems to do a better job. Things are a lot more stable, and I can wiggle these and my displays don't do weird things. And also I have a box of it. I can just cut, strip, put in, and just do it, and have plenty of super cheap jumper cable for this project. Stripped leads, and you'll see some of these flying around here, like these. It's this standard boxed stuff, or even Ethernet. Seems to do a better job, generally speaking, of making connections and staying put than these DuPont leads here do. And if you look down here, which I'll be telling you in a minute what this is, if you look down here, I wiggle these, and the lights go all wonky and stuff. But when I wiggle these, the signal lights for these, they stay put. They don't do anything weird. So I really do think that those do a better job than these DuPont plug leads. I've had a lot of power bus issues. If you look, I have power connections crossing. These green ones are green for ground, or 0 volts or whatever. I've got these all over the frickin' place, trying to stabilize the power distribution. I had run everything from this guy, this extra strip in here I put in here as a power bus. That didn't help, so I just ran flying leads all over the place. I think it all comes down to the fact that breadboards kind of suck at distributing something in something as complex as this, or I have just really crappy breadboards. I don't know. Since this isn't a permanent project in breadboard form, we may be solving those problems either with PCBing the different pieces of the project in sections as I go, and that'll be interesting to look at too, to just, to design, do my first PCB design with the etching and all of that magic, or I might temporarily graduate to one of those pre-made breadboards where it's just one unit with all of the pins and stuff and the power leads and all of that magic. I don't know. I haven't decided yet. So, learned a lot since the last episode, which is good, which helped me get this thing stable to the point where I can just turn it on, and 95% of the time it just turns on and initializes directly. So now that I've gone through all that, let's look at all of these different pieces I have put together and get an idea of what is actually going on with this machine. So let's go through this section right here. The first piece here is this. This is a ROM chip. This is the same ROM chip I had used for the hex display. And you can see I maybe is that off camera? It's just barely off camera. I yanked this chip out and put it down here, just so I'd have plenty of ROM space for when I was doing my design to put code or whatever. This is a 128 kilobyte ROM. That is twice as much memory as the 6502 can even address, but I figure with some clever trickery with the address lines, we might be able to do some bank switching stuff in the future, maybe? We'll see. This, obviously, or maybe not obviously if you're not familiar with what's going on here, has all these fly leads, and I'll go through these briefly. If you look up here at the 6502, it can be kind of hard to see through this, but that I've cross-linked the 6502 address and data buses over onto this breadboard here, and then cross-linked that entire with the orange wires that you can kind of see buried in here straight across to the other side. That gives me plenty of tie points for connecting into the address and data buses. And so what we have is on the far left end here the 8 lines for the data bus, and then the right side we have the 16 lines for the address bus, and those just jump across straight from the 6502 onto there. Of course, I'm pulling off the address bus for here. Something I'm not sure if I talked about this in the last episode or showed it, but I also have an extra display up here I added, just a copy of half of this display that shows me the data bus, and that connects to the data bus over here, right through here, right through this rainbow cable. Back to the ROM. We've got our address lines are the blue ones here, and our data lines are the green ones here. So dependent on what oh, hold on, I got a little glitch. There we go. See, power bus is a little weird, funky on this, doesn't it? It's fidgety. You touch things at the wrong time and it goes weird. So depending on what's on the on the address bus, it fetches the right data onto the data bus, in or out, or whatever. This chip over here is our ROM, or our RAM. The ROM can't do anything by itself. I mean, it can, but it's kind of stupid, if you don't have some RAM to actually make the machine functional. So this is a RAM chip. Now, so this is the permanent ROM chip I'm going to be using, but this is not the permanent RAM chip I'm going to be using. This is a little tiny 2 kilobyte static ROM that I stole out of my Kpro 1, 2, 4, whatever that thing is. You've probably seen my Kpro videos on restoring that. If you haven't, go through and find them. They're pretty neat. But yeah, this just comes out of the memory, or the video circuitry of the Kpro. I just stole it because I had it. I didn't feel like going to the expense right now while I was playing around of going out and buying the parts yet. But we'll be getting that replaced with an actual part. And of course, we have the same situation going on here. The blue lines here are our address bus, which goes over to this side, and then the Ethernet lines here, the orange, green, blue, brown, are our data bus, and they come over here. Some other signal lines I have going on with the RAM and ROM. We have this wire right here, which is connected up similarly to this wire right here. This is our read-write line. So what that allows us to do is when that is pulled, I believe, high. When that's pulled high, it is reading, and when it's pulled low, it wants to write out, which basically is a bus direction flag, if you want to call it that way. And that ties through this inverter that I have as part of the reset circuit. Why don't we go ahead and reuse that chip? It's there. It's got 3 extra inverters in it. It's close to the CPU. We might as well use it. It inverts that signal. Since both of these chips expect their read sense line, or whatever it's called, they expect it to both be low when active. I invert this. So the CPU, when it's in write mode, when it's expecting to push to RAM, it pulls this high. Basically, it pulls this high to disconnect the ROM. And I'll show you on the schematic exactly what line that is in a second. I have these 2 other yellow lines coming off this. Oh wow, I moved it around. I have these 2 yellow lines here coming off of this wonderful circuit, which I'll be getting into in a moment. These are our RAM and ROM selection lines. Basically, in combination with the read-write lines, they help us select whether the ROM is the active chip or the RAM is the active chip. Why are all these yellow lines important? Well, because you can't have both the ROM and the RAM active on the bus at the same time. If you do, what happens is you get bus contention. You get two devices either trying to write or read from the bus at the same time. They both try to do the same thing at the same time. The CPU gets confused about what data might be on the bus or what it expects, and the machine crashes and it goes off into La La Land forever. That's something we're trying to avoid. So that's what these select lines allow us to do. Now let's dig into this big thing right here, this mess, if this over here isn't a mess of enough. This right here is our address decoder. It's our simple baby's first address decoder. Basically what we have here is a means to detect, with the way I have it wired up right now, what segment of memory, based on this digit, the most significant nibble of the most significant 4 bits of the address, where we are in the memory scape, so to speak. I believe this will probably be all I will need in address decoding, with the exception of maybe another little add-on circuit to deal with I/O, the I/O space separately, but we'll see. And basically, what this is it just allows us to determine what that is. So let's take a look at that. What we've got here are a couple of 74LS138s. I did that from memory. The 138 is a 3 to 8 decoder. Basically, it'll take 3 input bits and light a single output line, which you can see some of those down here. It will light a single output line that is equivalent to the number it's receiving in bits. So if they're all if all the bits are lit, are solid, they're all lit, what it'll do, it will pull low the 8th input. So it encodes, you can say it encodes 0 to 7 or 1 to 8, however you want to do it. But basically, if it's all 0, well, it's 0 to 7. If it's all zeros, your 0th light will be lit here. And as we can see, this is 0, so this 0th light is out. Now we have these two of these tied together because this is a 4-bit value. These are 3-bit decoders. And I happen to have 3-bit decoders, and I didn't want to go looking for 4 to 16 specialized chips that would probably cost a lot of money. I mean, these cost a few cents a piece, big frickin' deal. I have a bin of them right over here. So let's wire up a circuit that combines the two into a 4 to 16. That's actually pretty simple. What we do is we use the combinatorial inputs that are at the far end to sense the highest bit. If the highest bit is low, this chip gets activated, this chip gets deactivated, and this chip doesn't do anything. However, if the high bit is high, it flips the other way. This chip gets deactivated, this is activated. And what it's doing, both these chips are effectively just decoding the lowest 3 bits of that 4-bit value. However, each chip individually gets basically banked in or out based on that highest bit. So it allows us to decode 4-bit, 16 different signals from 4 inputs. And so that's how that goes here. If you look very carefully, we've got the highest 4 bits of our address bus on these flyover leads coming into here, and then it all cross connects. We got a couple other little chips in here. These are NAND to NAND gates. These are combinatorial simple logic gates. It is a, well, gosh, what is that? That's a 74LS00 and a 74LS08, I think, or an 04. I don't remember. Hey, let's look at the schematic. It will remind Joe what he designed. It's an 08, yes. So basically, these are NAND to NAND gates. What these allow us to do, then, are to combine, if you look very carefully, the input of different signals on this bus to determine what our ROM select and RAM select outputs are. And you can see they're connected to these 2 different chips. What that does is allows us to bank in specific areas of RAM for whole chips. Now, why is that important? It's a little bit complicated because my explanation of logic isn't that great because my brain is like Swiss cheese after shotgun blast, but bear with me. What we have is I want this ROM to be active between the memory values of E0 whatever to FF whatever, basically from E0 all the way up to the end. Because I'm decoding this as my selection digit, what that means is I need to, that's these two lights here, this is E and F. And you can see I've got this double flyover lead here to select on that. Comes into here and helps me select that. By pulling both of these into, the OR gate here, which I believe is what the 08 is, I pull this into this OR gate, and that, or it might be an, I see I'm bad at logic, whatever 74LS08 is. If you're a real nerd out there, you know what it is, and you're laughing at me in the comments right now. That's okay. So basically, though, it comes into this chip here, and it says if either, it's got to be an OR gate, if either of these are lit, or really out, I mean, it's a negation, it's a low value, but if either of these are negative, it will pull this line low, or really this line, and you can see with the way it's lit, because this line is lit, that means this is high. Because this is high, that means this chip is deselected. I then pass that signal across to this chip, which is really just combined in these two. It's really just the opposite of that. What it's saying is, if these two are lit in any form or fashion, either of those, no matter what they are, I could probably do this a little simpler, but bear with me, I'm learning. If either of these are lit, ever, more specifically, or if either of the, they both have to be lit, effectively, if either of these are off, what that does is that it then pulls this line low, which then goes into the RAM chip, which then selects the RAM chip. So this, our address decoder, allows us to pick what value we want on this to determine which one of these chips gets selected. Now, with this simple decoding output, I can go through whatever segment of memory, I'm calling this segments since this is a page, it's not a whole bank, it's just a segment. I can select on this segment of memory and decide what chips to swap in and out by wiring through combinatorial logic. This section up here is really what our address decoder actually is. And this is just picking off those signals, then doing something with the signals. So eventually down the road, I'll be able to do that. If I wanted to say I wanted, I don't know, D0 to DF, for example, to be address space, all I would have to do is select on signal D here and go through and say, if D is out, D is low, that deselects all the other chips and selects specifically, it will just deselect all of the chips really, and it will select in my I/O device space that I can then have another set of circuitry that says, okay, well, if it's this area, it's this chip, and if that's area, that chip, whatever. I already have, the EO to FF, the E and F decoded. I already have 0 to E decoded. By the way, I did this, but I could eventually set it up to separately decode however I want. I could pull off more of the address lines after this is decoded. I could have a second address decoder that only is activated when, say, the I/O space is activated, and then I could pull off other address lines to say, okay, well, we're in this part of the address space, we're accessing this part of the address bus, the sound chip has to be activated, or the video chip has to be activated, or whatever we end up doing. So that's how we can do that. So, I've squawked on long enough. Let's just show exactly what I've got programmed in here. Now, the machine is not actually doing very much at all, but I wanted to see if we could demonstrate that. Now, keep in mind, wires are a little bit squirrely, so it might take me a little while to get this up and running. We may have to do a jump cut if I'm moving this stuff around and it gets grumpy. So right now, you know, when we do a reset, all we see is 0, 2, 0, and something. And then these just look like they're showing 8s, kind of dim 8s. And the reason being is, if you look in here very carefully, right in there, I have this running at 1 megahertz. The machine is right now running at full speed. It's kind of an achievement of itself. I got RAM, ROM, address decoder, and everything running at the full 1 megahertz. So, bonus! But in order to show you what's actually going on, we want to slow the machine down. So I'm going to see if I can do this while the power is on. If I hold down the reset button while I move us to one of the slower thingies, I should be able to do that. You see that? Let me hit the reset button and you can look again at what this is doing. Watch this one here. See that? Reset, reset, and it goes back up to the 208-ish thing. Well, what is it doing? Now, remember what I said about how I have the address space set up. The RAM is at the basically at the low end of RAM of the address space. It's 0 up. And of course, you know, it repeats because I've got bits in there I'm not selecting, but it's 0 to 2K effectively. And this I have address selected specifically at E to F. So if you look carefully, and I'll slow it down here in a minute so you can see it really well, but see it's popping between, I got a little bit of a glitch there. Yeah, see, I got some weirdness going on. There we go. It pops through E and then to blah, 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 blah. So what it's doing is it's starting in ROM, as it should, and then does stuff with RAM, then it's jumping up into the RAM space. So basically what I have is I have it properly bootstrapping a code and then running the code in RAM. So let's slow that down a lot more. So let's slow that down to way, way super low speed. If I can get it plugged in here. And let's let it go. So you're going to see it start at the E. It's going to dig through here. Watch. 206. What's it doing? I'll tell you what it's doing. It's copying a very simple routine out of ROM into RAM. And you can see it's counting these RAM 204. It's counting them backwards because I'm just using a simple decrement, an indexed X decrement to just run through that and dump that all down into the RAM. Watch it. It's going to pop another one. Two. Yep, there you go. You notice while it's doing this, every time it pops down to the 2s, this light comes on. What that light means is effectively it is inhibiting this chip because the read-write line goes low. Basically, it's saying, "Hey, hi, read-write line. I'm trying to write to the RAM. You need to get the heck out of my face." And that's what it does. It deselects this. It goes through the combinatorial logic here, the inverter, and comes back here and allows the write line to come on to write to this. Now, of course, what you see, it's up in the 200s, the 0200 area. What is this code doing? It's just spinning in a loop. It will spin in that loop forever. It basically counts, it decrements X, I think, from 255 to 0. Once it equals 0, it jumps back to reinitializing X to 255 and repeats it over and over again. But basically, it just sits there in a loop and runs forever. But I thought that was an effective way for me to show that I was able to properly both select ROM and RAM and select the read-write line so that we could write to the RAM space without writing to the ROM space. Let's show that again so we can properly show this lighting up here. We'll do a reset on that. It's going to reinitialize the processor. CD E0, 1, 2, 3. Now watch it when it goes to, it says 200. There. See that light? That means it's disinhibiting, or it's inhibiting this one and enabling this chip specifically. This is This is the read select line. Basically, it tells this chip, go high impedance and don't put anything on the bus. And then this, that allows the CPU to actually put a value on the bus. It comes over here in write mode to tell the chip, hey, you can do that. Now, let's look at the address selector. I'll go ahead and reset it again so we can see that. You guys have probably been watching it. Now, there we are. When we're up in the F's and E's, you can see it's selected up here. And our chip select is this one. But when it goes to the 200s, wait for it. There it is. It selects the other chip. Now, of course, these are inverted. It's select low, not select high, but it allows us to see that the address, our ROM select and RAM select lines are being picked properly, and then you can also see that we are decoding this value properly with the address decoder. That's pretty much all I have right now with the design. I wanted to do a very basic setup of RAM and ROM to make sure that all of my signal selection was correct, my address decoding was correct, and to really wrap my head around the theory of what was going on. Let's take a second out, though, to show you the schematic, if we can get that properly perched up here under the camera. Oh my gosh, I'm dropping stuff all over the place. It's a nightmare. Let's move that down. Let's focus you. There we go. So, here's the schematic as we have it. Let's go through all these lines and actually use real terminology, shall we? This is our CPU. This is our 6502. And I'm using address signal flags here to show the connections to those. So it allows me to be more flexible in how I lay this out and not spend hours and hours and hours drawing lines from things to other things. I can just put the flag on it and be like, oh, A connects to A, connects to A. This hasn't changed too much from the previous schematic, other than to show now we have all of the address lines, all of the data lines, the read-write line, and all of those flagged out to show that they're actually connected out to the rest of the system. This right here is our address decoder as it is right now. These are our two LS138s. Basically, what we have here is, this is our, it selects the lowest 3 bits, and then this is all, depends on what the input of 15 is. Same down here, the select line depends on what 15 is. So, when 15 is high, it deselects this, and here when 15 is high, it selects this. So basically it's just turning whole chips on and off based on bit 15. And then it's just actually, each chip is actually decoding 12 through 14, which is really all it can decode. But this actually is a pretty slick setup. It allows you to chain whole chunks of these together in a full decoder. You could put a buttload of these together and and decode every address location if you wanted to. I mean, you could do all 65,000 of them. It would be a friggin' nightmare. It'd be an absolute crap show, but you could do it. Of course, all this does is connect to the address lines, and then it allows us to decode our segment E and F. The rest of these right now I'm showing as no connection, but these go to segment D through 0. And they go to those, it goes to the lights over here, basically just to show me that it's doing whatever it is that it's doing. Refocus because I move stuff around. Over here are our different selections. Selection circuits. So let's start with this, because this is actually part of the address decoder board. We've got a not and an and. If either E or F are low, if either one of them are low, that means we don't want to select RAM. So both of these have to be high in order for it to output a signal here. The ROM is the exact opposite. Both of them have to be low for it to output a signal here. And that's basically what it does, and it allows us to select either between the RAM chip and the ROM chip. Now, that's, RAM select, ROM select. This is ROM OE, or what I call ROM output enable. Effectively, what that also does is that here ties to the read-write line here of the CPU, so it allows it to say if the line is low for write, it comes in here, it's low, it gets negated and brought high, which then goes into one of the selections here on the ROM chip to tell it what to do. So let's pull that into a little better focus so we can see how those signals talk to our chips. So let's look at the ROM chip here. This is pretty straightforward. It's just tying into the address lines and the data lines so we can select what we're doing. I have these upper selection of lines because we're not reading that high part of that chip. I have these just tied to ground. They're tied to 0, so that they don't float. I'm not using anything up in those high memory locations, but that's fine. Everything in this chip is indexed to 0 up. Now theoretically, I could just wire this directly into the bus, tie 16 to ground, and actually start my memory inside this chip at E000 and leave everything below it blank. It might make selection of the things a little bit easier, but I went the hard route. Why not? And here are our chip selections. So we have the chip enable is selected to ROM select. So when ROM select is low, this chip is selected and allowed to output data. Except when this is high. Output enable also has to be low in order for this chip to be selected to output. So basically, both of these have to be low in order for this chip to do anything. So that allows us to say when the ROM select is low, we're basically when we're in the proper part of RAM, or proper part of the memory space, and the CPU is not writing something to the bus. This, we go tri-state. Effectively, this thing goes to high impedance. It doesn't pull current, it doesn't push current. It just kind of disconnects its inputs entirely, which allows whatever else is on the bus to communicate on the bus without contention. So that's what that does. ROM cell going down here, and ROM output enable going to OE here. Here's our RAM chip. Of course, this is going to change eventually because we're going to be putting a bigger RAM chip in there. I don't know if I want to do a couple of 32K chips or a 128K. Depends on what I'm going to be able to get. I'm going to have to get some newer, fancier static RAM. They don't really have the older chips available as much, so we'll figure that out later. But yeah, same thing here. We got our address lines, we have our data lines, pretty straightforward, and then we have these 3 lines here. Now I have both output enable and chip select tied to RAM select. When RAM is selected at all, if RAM is selected, it basically allows the chip to do whatever it needs to do. And that's really the easiest way to do it. And if you look at the data sheet, that's perfectly fine. Now, the write enable is connected to read write, which is over here. It comes straight out. It comes directly out of the processor. So when, this is written, when this is low and all the other 2 are low, that means, hey, I can receive, I will suck in whatever's on the data bus into how I'm being addressed here, and it goes pink, and it does the magic. However, the way this combinatorial magic works, if this write enable is low, meaning, hey, I'm allowed to receive data, but the other circuit, the other items are high for whatever reason. Say we're out and we're writing to a different memory location, like in the I/O space. This read-write may go low, but these guys are going to be high because of the way the address selector is doing it, the address decoder. That means this chip is just going to ignore what's on the bus. It'll go high impedance, just like the ROM, and it'll just ignore it, and that's it. So we have, we got the basics of our CPU, our address decoder system working, and our RAM and ROM working. So that is pretty friggin' slick. Let's turn this back on and see if it will you auto initialize for me, or will you be grumpy? of course, hold on, let's let it go. Yay, it auto-initialized for me. It's been really persnickety. Again, that goes back to I've got power bus distribution issues. It's almost universally power bus. When it goes funky like this, I can wiggle mostly the ground lines and it comes back. I can do a reset and it'll come back to life. It's weird. I don't know. Hopefully we'll be correcting that problem before we get too much further in the project. So, you know, where are we going next on this project? Well, we want to be setting up proper external input and output communications with this. Now that I have the address decoder and I have RAM and ROM put in place, we can start doing that. And I already got my pieces and parts. Look, we got a 6551. I stole out of hold on, I'll tell you where I stole it out of. Stole out of a Super Serial card. And I've got my crystal to drive that. So we should be able to do a very basic serial protocol. Connect it up to the bus, give it the right program, and I should be able to use my computer and serial directly into it and start actually using it as a real computer. That would be cool. The other thing, other major change I'm planning for next portion would be the RAM chip. You know, I'm just borrowing this chip out of my oh gosh, what's it called? Out of the K Pro 124816, whatever the heck frickin' model the thing is, to do this. So I'll be looking at getting a proper RAM chip so that we can have the final design and we can get things hashed out exactly how we want it configured. I'm going to be working on the memory map. Since we have a proper address decoder, we can start designing that. You know, the idea, and you can see I have some of it planned already. We're starting at 2 here for our code execution. The pages 0 and 1 are our 0 page for 0 page fast indexed mode on the 6502. You know, it gives you those 256 free registers, if you want to, however you want to call it. And then we have the page 1, which is the stack. Those are basically kind of sacrosanct areas. You can put code there if you never use the stack or the 0 page to do anything. But as you can see, I'm already preparing to just ignore that area so that future code, whether I write my own code or I get some pre-written code and modify it for my means and dump it on there, it's the system is already set up and ready to take care of that. 02, as we have, through CF, I think is going to be my user space or just my RAM. 02 through CF will just be my RAM area where we can load applications and run them. I think we're going to have D0, the entire D space, D0 through DF, being I/O. That's quite a bit of space to be able to do things with. That's what, a whole K or 2K of space or something like that. So I think that's going to be plenty of area for us to hook in I/O, especially if we're using something like a 6526 or something similar to that, that's got a buttload of parallel and serial input and output pins. You can chain those things together and with a single chip address an absolute crap ton of different devices. So, you know, we'll probably have 1 or 2 of those. We're going to have probably 1 or 2 sound chips. Ooh, chip tunes. And then some sort of video input-output system. I'm not exactly sure how I'm going to do that yet. I have an idea, but it depends on whether or not I can get my hands on the silicon. And then, of course, you know, we're going to have the 6551, maybe 1 or 2 of those for serial input-output. I probably only need 1. I'm not planning any sort of expansible I/O with this, although we could make a whole chunk of space, say C0 through CF, kind of like it does on the Apple II, as just, if you want to call it, slot memory space for putting in your own cards and doing whatever the heck you want. You know, we would just present the whole bus to the slot and be like, have at it, have fun with that. But I don't think I'm going to do that. That's not really the point of my design. I'm not trying to do an Apple II. I'm just trying to see what kind of magic it can make happen. And then, you know, the E0 through FF, which we already have kind of planned out here, is going to be our primary ROM space. That'll probably be plenty for what I need. Although, you know, look at a lot of other computers, they need a lot more space than that to have all the ROM they need to do what they need to do. If I'm going to be putting Tiny Basic or something in here, I don't know. Well, I might write my own language. I might not put any sort of programming language in it at all. We might load that with a cartridge, quote unquote. Maybe, I don't know. We'll figure it out as we go. Yeah, and then the final thing I'll probably want to be doing is, and hey, look what we got here, proto boards. I may be doing it with those. I may be doing it with actual etched PCBs. I don't know. But start proto boarding some of this stuff, or PCBing some of this stuff as those pieces of the design finalize, so that we can improve the stability of pieces and parts as we go. Because as I said in the very beginning, I'm designing this with nothing more than a multimeter and the output on my power supply and the signal lights that I'm putting in here as I go, just to make sure things work the way I expect. And the fewer stupid little bugs, like dealing with the power bus being a butthead, that I have to deal with, the better it's going to be as the system gets more complex as I go on. What else? Well, we want to give you some freebies. So check out the links below in the description. I'm going to give you a full a download of the full schematic here. So if you want to follow along at home, you can do that. I'm also going to do a full dump of all the ROMs, of both this ROM here and my my hexadecimal decoder. So if you wanted to, I don't know, build the circuit yourself, you could go ahead and do that. And you can play around with that at home if you want, and if you find ways to improve it. If you see glitches or issues, things I did wrong, you know, you can call me out in the comments and say, hey, you moron, you did something wrong, and I'll be like, thanks for letting me know, and then we'll be all good. Well, that's all for today's episode. I really hope you enjoyed it. If you did, make sure you hit the like button or subscribe, and remember that 8 bits are all you need.